Welcome, ladies and gentlemen, to this video lecture. Let's take a look at this theorem. This theorem is extremely important, so I will call this, let's say, probably the most important theorem of this section. Why is it so important? Because it will allow us in our it will allow us to determine how many terms we need in our Taylor polynomial to get an approximation for a function value up to a number of digits. So for example, let's say we want to compute the sine of 1, and we want an approximation up to, let's say, 100 digits. This theorem will allow us to determine how many terms we need in our Taylor polynomial to be able to compute the sine of 1 correct up to 100 digits. So this is why this theorem is extremely important. So let's read this theorem. So we let n be any natural number, and we have an open interval I, and we have a function that is defined on I, and its n plus first derivative is continuous on I. Then we denote by Pn the nth Taylor polynomial of f about a. Then for any x in this interval on which f is defined, if there is a constant mx, so that we can bound the absolute value of the n plus first derivative of f for all t between a and x, then we can give a bound for the absolute value of the error. So remember, the absolute value of the error, this is the distance for the distance between the actual function value at x and the approximation given by the Taylor polynomial. And this bound, or this error, is always less than or equal to this expression. And if you look here, there is nothing very difficult to compute here. You've got this constant here, this factorial, and this expression, which is just the distance from x to a to the power n plus 1. So there's nothing particularly difficult to compute here on the right, and this will give us a bound for the absolute value of the error. Okay, so let us prove this theorem. So, proof. There are two cases. There's the case when x is greater than a and x is less than a. So we will consider this case. This case we will leave as an exercise. So let x be greater than a, and now what do we want to show? We want to show if there exists, if there exists such a constant satisfying this, then we want to get this inequality. So we will assume there exists some positive or non-negative number mx satisfying the following. So the absolute value of the n plus first derivative of f of x is less than or equal to mx for all t in the interval from a to x. Okay, then let us just expand this this absolute value. So we can say that this is less than m of x, this is less than minus m of x. But since x is bigger than a, actually let's write it this way, a is less than x, for all t between a and x, we've got that x minus t to the n plus 1 is actually positive. And therefore, if we take this chain of inequalities and we multiply everywhere by this number, the direction of our inequalities will not change. So we obtain minus mx, x minus t to the power n plus 1 is less than or equal to f n plus 1 at t multiplied with x minus t n plus 1, which is less than or equal to what we have on that side, mx x minus t over n plus 1. But also n factorial is also positive, so we can also multiply throughout by 1 over n factorial, and the direction of our inequalities will not change. So this is the same as when we divide everywhere by n factorial. Okay, and now by theorem A1-10-1, the integral is monotone, so if we take the integral everywhere over the interval from a to x, our inequalities do not change direction. So what do we obtain? Mx over n factorial, integral from a to x of x minus t to the power n dt. This is going to be less than ax f n plus 1 t over n factorial x minus t n dt, which is less than or equal to mx over n factorial, integral from a to x minus t to the power n dt. But now we notice here from our previous theorem, this expression is exactly e of n. And these integrals are not difficult to compute. So finally we obtain since en of x is equal to integral from a to x of f n plus 1 Where does this come from? This comes from our previous theorem. We obtain, since that is true, we get e to the n x is less than or equal to mx over n plus 1 factorial x minus a to the power n plus 1, and on the other side minus mx n plus 1 over n plus 1 factorial x minus a n plus 1. And now, since these expressions are positive anyway, since x is, we assume that x is greater than a, so x minus a is positive anyway, so it doesn't change anything if we replace these brackets by absolute values. And therefore, if we put everything together, we see En is less than minus this, is greater than or equal to minus that, and less than plus that. So we get the absolute value of En is less than mx x minus a to the power n plus 1 over n plus 1 factorial. And that ends that proof. And now in the next video, we will show how to use this theorem to determine how many terms you need in your Taylor polynomial to be able to get an approximation to the value that you want as accurately as you want. So let's say, for example, you want to compute the sine of 1 accurate to 1,000 digits. Question becomes, how many terms do you need in your Taylor polynomial to be able to compute the sine of 1 accurate to 1,000 digits? And that we will do in our next lectures. I will see you in the next one.